Hello, welcome to the 5th episode of Automat DEVLOGs. Today we are going to talk about how we are doing animations within Automat. And we will do this using a demo of the most recent instruction library object. This is a very tall stack of cards, which are instructions that can be combined together to do stuff in Automat. They are grouped into categories, which we can traverse by selecting those flowers and select instructions by scrolling through the cards. We can also select input and output registers using this table at the bottom. So that now the decrement instruction selects the BX register, which is the box. The way we do animations in Automat is that first we think of two things. It's like backend and frontend in web development. All of the objects that you see on the screen, they have a backend which contains the logic of the object, and the frontend which deals with animation and rendering of the object. We do this split because the backend, the objects themselves, they may have to perform heavy calculations. They may need time to compute some stuff. And because of that, they have to be multi-threaded. They deal with mutexes, with locking, and the activity of objects can happen in parallel. If you imagine a very large, complex program with tons of objects, they don't block each other. They can all run in parallel without any communication. It's different with frontend, because on the front end, we actually want to respond to the actions of the user. So when the mouse moves over the screen, we want to render the object in its most recent state. We want to minimize the latency between input of the user and the stuff that's rendered on the screen. And this minimalization of latency, it tends to work nicely when we do this in a single-threaded fashion. When we render stuff, we also don't just render everything. We try to plan ahead. So because the view of Automat can be divided into those nice widgets, we can also do some accounting and, for example, compute how long it takes to render a single object. You can see this when I zoom out and zoom back in. You may see a pixelation effect, right? This is one of the tricks that we are using to keep the response time low. If we cannot render the object in time, and when we have to re-render a lot of objects, it's not possible. We render as much as we can, and then we just flash the frame, we composite the old texture, whatever, just to keep the latency low. And you can see this, that even if I do all this, even though things are pixelated, I can still move stuff around and it's very responsive. The way we do this frame packing is actually fairly complex, maybe beyond the scope of this single devlog, but for each object, for each widget, we track its animation state so that we know whether it's animating or the animation stopped, and we know how long it was last re-rendered, at what resolution, so we can make conscious decisions about which part of the image we want to re-render and how this will affect the rendering time so that we don't exceed 16 milliseconds. The entities that live in the backend we call objects, and entities that live in the frontend we call widgets. Objects are very simple, actually. They require some synchronization mechanism like mutexes or atomics, and they hold just a simple state. This is the single source of truth for the logic of Automat, for the core. This is the engine. And the widgets, on the other hand, they are the fuzzy bit which shows this stuff. They hold all the bits necessary for animating stuff. So let's take a look at how the instruction library works. And the object part is this. It holds a very simple state. There is a mutex used for synchronization. It holds the category, which is currently selected as pair of integers. It holds the filters for the registers that we want to read from or write to. and the width of operation that we want to use. And all of the instructions that we compute are held in this collection. So this is the source of truth for this widget. This is not enough to actually render a nicely animated object. For this we will need a lot more variables. This is what widgets are for. Inside widget, we hold a pointer to the object, and for each component of this object, we hold extra state, which is necessary to animate it. For cards, we hold, for example, the angle that the card is at. We hold the position from the object where it was found in, and a bunch of extra variables. This is the most important one. This is the one that we use for throwing the card below the deck. We also have state for example, hovering over the deck of cards, which twists it a little. For the registers at the bottom, we hold animations related to the button being hovered and pressed. So when I move my mouse here, you can see those blinking lights and circle. This angle here is stored in this float variable, and we hold them for each button here. Similarly, for categories, which are those flowers, we hold the state of the growth, whether it's shaking, whether the leaf is discolored or not, whether it's hovered. We're also caching some values here for faster execution of other bits of code, but it's totally unnecessary. We could recompute them just as well. So in total, if you look at our widget, we require 648 bytes. For the instruction library, which is the ground truth object, it's just 216 bytes. So the objects are lightweight, they are fast, they don't involve any animations, and widgets are slightly heavier, they hold the animation state. However, they don't hold the textures, they don't hold the actual contents, the stuff that is being kind of displayed on screen. This is because there is another layer of indirection. Widgets, when they operate, they have basically two methods which are key to them working. The first is called tick. This is the method of the widget which advances animation. When we animate a widget, we call this method, and this method tells us whether the animation finished or not, or whether we are still animating. This is something that we are using to suspend animation. So when everything on the screen finished animation, we are pausing the animation. You can see that the millisecond counter is now frozen basically. But when I move it, for example here, it's moving, like it's 16 milliseconds and it's moving. When I stop moving my mouse, it will eventually freeze when the animation stabilizes. Yeah. Once the animation is done, we can draw the current state of the widget using the draw function. And this function, even though it's called draw, it doesn't actually draw anything. It just records the drawing commands into this canvas object. Then, after we have recorded all of the draw commands from all of the widgets, this is when actual rendering happens. And rendering happens on yet another thread. So this whole process, I said that rendering is single-threaded. It's not quite single-threaded. You can actually do this ticking and drawing in parallel, and then rendering, which is the actual rasterization of the drawing commands, can also happen in parallel. It can also happen on a totally different machine, because this state, this list of drawing commands, it can actually be serialized and sent over to a different machine. It's something that we are not using, at least not yet, but we could. So to summarize, Automat uses a rendering architecture which actually separates this whole system into two parts. Engine, which is multi-threaded, which is meant for bulk activity, for heavy compute, and rendering layer, the front end, where we have widgets, and they deal with animation. They take care of smoothly animating those values, serializing the rendering commands, and then sending them out to the frame packing algorithm, which plans what widgets we will re-render in the subsequent frame, and re-renders them and composites them on screen. So it's fairly complex, but it produces actually a nice API that we can use to build individual objects. So that's it for today. See you next week. Bye.